So in the Beer-Lambert law, we have this equation up here. A represents the absorptivity, the E, or the absorbance. The epsilon is going to represent the molar absorptivity, B is going to represent the path length, and C is going to represent the concentration. So what that means is that on the graph, we have Y. On the y-axis, we have absorbance, and on the x-axis, we have concentration. So in the equation, A is going to equal what y is on the graph. C is going to equal what x is on the graph, because that's concentration and absorbance. E is molar absorptivity, which is the slope of the graph of A plotted against C, which is absorbance plotted against concentration. B, the path length, is always just going to be 1 centimeter, so it cancels out in the equation, and we get an equation similar to a line where we have y is equal to mx plus 0, 0 being the y-intercept, and all of these values matching up to the ones above it. So the issue that occurs when failing to zero the machine before with a blank is that you get incorrect absorbance values. When you zero the machine, you take out the account of a pure water sample, which means that whenever you measure after you've zeroed on a blank, it's only measuring the absorptivity of whatever is in the solution. So if one fails to zero with a blank beforehand, then the values won't be accurate to only what is ever in the solution.
In our two examples, we picked the lambda max and another point lower than that. Basically, we have to pick lambda max, which is the point of highest absorbance for the stock solution. Over here, it kind of looks like this one's the lambda max, but it's a local minimum, or it's a local maximum. So it's not really the highest point of absorbance across all wavelengths. The reason why we pick lambda max is because it's going to give us the most clear-cut difference between the absorbance of different concentrations of whatever we're measuring. So say we picked this point, which is the absorbance for the stock solution at this point is close to, if not 0. So our graph would end up looking like this for all our measured concentrations. The slope would be close to 0, so there would be almost no measurable difference. However, if we pick the point with the highest absorbance, the lambda max, then we would get a defined linear expression, which would give us clear differences in the concentration, allowing us to find different concentrations for...
So right here, Justin is adding the blank cuvette into the spectrophotometer to make sure that we have it zeroed. And then we are clicking 0 to make sure that the machine knows where it needs to be. So here, Geoffrey is taking our stock solution and wiping the sides clean with a chem wipe. He is then adding it, or placing it into the spectrophotometer with the clean sides clear in the beam and closing the lid. And then we are running the absorbency test to see what our results will be. Here we have Trevor recording the absorbance of the stock into a notebook, taking out the sample. And then cleaning up all of our since we are done, and closing out of the program. So here we have our calculations for determining how much of each sample we needed to put into the next dilution over. And over here we have each solution, what its concentration is, and then the absorption based off the graph, or based off of the spectrophotometer.